welcome to the group discussion on the distance ladder by Kritika. Yash and I, Raghav, will be taking this. So, starting off, I don't think we have much to introduce. So, without further ado, I give you the chalk.
So, hello guys. Today we'll start off with smaller distances and with progress of the ladder. So, starting off simple and easy. Normal distances we all know how to measure, right? You hold the ruler and you hold it against anything that you want to measure. But now, let's say you want to measure something that you can't hold the ruler against. So, you have your earth. Any ideas on how we would go on measuring the radius, diameter, circumference of the earth?
Without using the book to find it, you have to actually measure it.
Any ideas? It doesn't have to be the right answer. Any intuitive thoughts?
I think you have an answer.
2 points. Go to 2 points go to opposite ends.
Okay.
And then look at a point that's something far away. You look at an exact point and use.
Good.
How do you know if 2 points are opposite without knowing the action?
That's a valid point. That's a very valid point.
But given the fact that we don't know how wide the earth is yet.
Yes.
And also, if you could figure out the radius, that will also prove that the earth is round.
So for now, we won't delve into why we think and know for a fact that the earth is round. Assuming that the earth is round, let's talk about how we can measure the radius. The flat earth was, as a matter of fact, another idea for a GD that we did not go through with. But yes. So what he hinted at is essentially some sort of a variation of geocentric parallax, which we'll explain in a while. Yes, thank you.
So, I'll present you the argument that Eratosthenes put forward and measured the radius of the earth. So, interesting fact, by the way, he wasn't even looking forward to different ways to measure the radius of the earth. He was in a library and he came across a book and he read an interesting fact that in Cepheid, a place in Greece, he saw that the shadow on a particular day is exactly 0. Like you have a deep well and even at the bottom of the well there is no shadow. Light exactly falls from the top of the. So he found that interesting and then he thought of, well, does that happen where he lives at Alexandria? The answer is no, it never happened. The reason why it happened at Cepheid is because it lied exactly on the Tropic of Cancer. So,
On the summer solstice, the sun was exactly at the zenith. If you guys have doubt as to why is the case, we can address that. But in general, on the summer solstice at the Tropic of Cancer, the sun would lie exactly at the zenith at noon.
What is the
So,
zenith?
Zenith is just like the exact. Exactly.
Kundan will help us visualize certain phenomena.
So he's our illustrator. And so yeah, continue.
So, he took Cepheid and Alexandria. Now, on the day on which the shadow at Cepheid is 0, at the same time, now we would ideally measure the shadow. So, the point was to measure the angle at which the sun is from the zenith at Alexandria at the same time at which the shadow at Cepheid is 0. But he couldn't possibly be taking 2 measurements at the same time, right? And you can't have conversation with an observer. Remember, this is happening around 200 BC, so long time ago. So what he did is, he did one measurement, he waited 1 year for the next solstice and then he performed the next measurement. So he went to Alexandria and he found out the angle that the sun made with respect to the zenith. This angle came out to be 7.2 degrees. Now, the point is, okay, so the angle subtended by what he assumed is the sun is quite far away. So the sun rays are coming parallel to each other, right? So the difference in the angle 7.2 degrees is the arc subtended by the distance between Alexandria and Cepheid at the center of the earth. Now 7.2 degrees is exactly 1/50th of 360 degrees. So we found out the distance between Alexandria and Cepheid. Now, how would you measure the distance between two places in 200 BC?
That's actually a very interesting question. How would you like even so like before talking about how we measure distances in the universe, it's interesting to think about how we measure the distances between two cities. You can't go with a ruler and be like,
You like ride a horse and see how many days it takes or something. Ride a horse and like see how many days it takes to like reach.
Exactly. So that's what he did precisely at that point of time. He knew how fast a camel traveled. So and also, I mean, that's not so he measured using two methods and verified using them that the answer was similar, so that his calculations weren't completely off. There were some people in those times that used to perform these calculations. There was a method as well. They had some wheels on their vehicles, and they would see how many times it would turn in the journey. Now, this is a measurement along with the camel measurement which was actually done. So he found out that the distance between these two places turned out to be 805 kilometers.
If there were mountains around there, they could also like go on top of a mountain, see what angle.
But it's a desert.
Sand dunes.
Interesting. Like using parallax for
Yes, you would need the height.
no, but honestly, like even if you go up on a mountain, you can't be like, "वो रहा मेरा शहर." It's a bit like
How
tough
accurate
to-
was this measurement?
There's a lot
How
of
accurate
light
was this measurement?
attenuation.
This
now.
measurement is not that accurate, which we will see soon. Why?
I mean, it depends a lot on the topography. वगैरह. Like, let's say you have a mountain where in the middle, then you like travel a lot more just for the same distance traveled.
I mean, the Earth isn't a sphere anyway, so.
Broad line.
Yes, just
Yes, that is what we look at by the end of the session.
So, since this is 1/50th of 360 degrees, you multiply this by 50 to get the circumference of the Earth, and he got a value of what? Okay. So surprisingly, that value is accurate within 1% error to the actual value that we have estimated at. Now, there were a few errors in this. Try to figure out where the errors might have been. One, which as we pointed out, that the camel measurement method, and because of the topography, it's not really an exact measurement. There was one other.
Cities weren't exactly.
Another error, the cities weren't exactly on the same longitude, so it's not accurate to consider them. Few more errors. Any ideas? Why?
So the sun logic only works if your cities are like this. Only then does with every degree you move along the earth, the sun move with the same degree. Case in point, if you were to move exactly along the equator with the same distance, the angle wouldn't change at all at the local. Okay. So if they are somewhat like this, there is some component of the movement which does not contribute to the change in angle of the sun.
How do you know the day of summer solstice? Like, can you calculate it?
They recorded even though measurements hadn't evolved, the records have been taken for a long time. So summer solstice will occur obviously 1 year after the day. So the dates those people were recording meticulously, like for long.
How many of you know what is the summer solstice?
I'm guessing
The
for
summer solstice is the time at which the sun is at its northernmost position in the sky. So even in those days, they could look at the shadow of a stick at noon, and they could find out when it is the shortest and brighter location. Something like that.
Also, then that should help you understand why the sun would be exactly overhead at the tropics at the solstice, right? Okay, so another error is now, even though this was very close to the tropic, this was like 30 kilometers away from the tropic, which caused an error. And small error was, well, we can't really measure the angle accurately as well. Even that has an error. The actual angle is 7.1 something.
How
So
did they measure the angle?
Okay, so there are actually a lot of ways of measuring the angle. One common way that is explored even during school is actually, I think the instrument they usually use for measuring the angle is a sextant. Yes. Okay, but one of the common models we use in school, and I think that is the sextant, but I'm not really sure, is essentially taking a protractor, having a huge weight attached to it, okay, and having something to point. So what you do is you actually you can do this way. Having this pointer, suppose you take this pointer, you point it at the place you want to measure the angle of, and you see it's the angle of. So if you tilt it, so if you point it somewhere, the protractor will make an angle this way. So essentially you need to measure this angle. So for measuring the angle of the sun, you can measure this angle and this angle. That is the distance between that is the angular distance between the zenith and the sun. So just by looking at what angle this thing is, you can find the angles. And if you make this protractor arbitrarily large, you can also get a lot of accuracy. Though the problem would be the primary precision problem would be whether you can point this exactly in the first place or not. It is not exactly a science to sun either.
also another quick word, this is half a degree. So you can,
What is half a degree?
your thumb at an arm's length.
Oh. Like just for eyeballing the distances in the sky, the angular distance in the sky, you can use
Roughly, obviously, everyone's.
Another way could be at this point, this is the horizon. You could have just kept a stick which is perfectly vertical, and these are the standards. This is the angle in which you are interested, 7.2 degrees. You would apply trigonometry on the length of the shadow and the length of the stick.
I mean, you could also keep a vertical stick and behind.
Vertical stick. At
This
that
may drop
point,
your essay.
at this point, this point, it's actually this is the person.
Okay.
And how are you determining at what point in the day you want to take the measurement?
I mean, like you can see ki at what point of time is the sun highest in the sky. Itna basic they had the science developed. So moving on, see we have a lot of distances to cover in this lecture. We are literally going to talk about how we measure the farthest distance in the galaxy. So moving on, once now we calculate the radius of the Earth. Now we are going to talk about how we calculate
Distance to the moon.
distance to the moon.
Okay. Before we present the idea, any idea you guys have? How will you extend your arguments to the moon? What?
Do you know the mass of the Earth?
Bro, Newton is like 1600.
No.
You don't.
Gravity was not discovered.
This is around the same time period as this guy. What I'm going to talk about.
So how could one possibly even say कि मतलब what is the difference between moon and a object that is infinitely far away? That is the question you need to think of. है ना? Your point is that the moon is at a finite distance and you need to measure that. So how would you distinguish an object which is at a finite distance from you from an object which is at an infinite distance from you? Parallax. Okay. So the fact that he's at a finite distance from me, I can see from the fact that if I take a side step, it changes in my vision. However, if I have a star at an infinite distance, मैं कितना भी हिलने की कोशिश करूँ, I never see the star move. So continue.
Okay, so the way we measure the distance to the moon, first of all, we'll be making our measurements on a lunar eclipse. I'll explain why.
I think recording is there.
I'll adjust.
Okay, so first of all, does everyone know what a lunar eclipse is? Show of hands who doesn't know, or show of hands who knows.
Doesn't know क्या
Some people don't know. Okay, so lunar eclipse occurs when the light going from sun to the moon is blocked by the earth. Now, lunar eclipse will always occur on a full moon night because full moon is when the moon is like the side of the moon facing the earth is fully illuminated. But then, why doesn't the lunar eclipse occur every month? Because you get a full moon every month, right? So why doesn't the lunar eclipse occur every month?
The moon is like the rotation is tilted.
The orbital plane of the moon is slightly tilted compared to the plane of the sun or plane. So it has to be exactly in the plane. So these points have to be exactly collinear for an eclipse to occur. Okay. So the argument presented here is so considering the sun is quite far away, we'll take the sun rays to be parallel. So we are not going to consider the angle at which. So parallel rays, Earth is going to cast like a region of shadow, right? The moon is going to move through the region. Now, does that give you any hint on how we are going to calculate the distance to the moon? Okay. Now, this people can obviously measure time, right? So you start measuring the time at which the total eclipse starts, like the center of the moon enters the umbra, and you record the time at which the center exits the umbra. Now this time came out to be around 3 hours. Right? Another thing is the moon takes 30 days to make one revolution around the earth, which is what 30 into 24, 720 hours, right?
Yes.
Okay, everyone agrees with this. Now you calculate this. This comes around to be 1.5 degrees. Like, get what I mean, right?
Yes.
The angle subtended. So another thing, as we measured angles earlier, people can obviously measure the angle subtended by the moon. The angle subtended by the moon was 0.5 degrees. Now,
So do you understand what the angle separated by the moon means? Just like if you take one end of the moon and the other end of the moon, the angle between them by your vision.
okay, so what that means is, since the rays were considered to be parallel, the diameter of the moon into 3 is the diameter of the earth. Okay? Because the rays, so follow me, the rays are coming parallel, right? If this thing is 1.5 degrees and moon itself is half a degree, So 3 moons will fit this angle. That's why the diameter of the moon is 1/3 of the diameter of the Earth. Okay, now we have the diameter of the moon. To find the radius, it's very easy now. You know the diameter of the moon, you know the angle subtended by it, so you just need to find out the radius, which is basic trigonometry.
So we made one of the simplest measurements that was known to man. Then
So just by measuring a few angles, we have moved away from the Earth. We moved to a different body.
Does the Earth's rotation contribute anything?
In 3 hours,
3 hours out of 24.
it does. So that's the point. Like they made the actual measure that when we're talking about such measurements, we often talk about the principle behind them. So accounting for effects that we already know of just requires a lot of more paperwork, but otherwise it can be done.
also, I mean, let's say you go closer to the pole, then
Yeah. So moving on.
okay, now think of how you extend to different bodies. Like, our argument here use the angular size of the moon, right? But let's say you pick a star. How can you measure the angular? Can you measure the angular size of that star, or what different idea you might have?
So okay. So now we have talked about हमारे घर के objects. We've talked about the Earth. We've talked about the Moon. So now we're gonna start getting farther away from the solar system. So starting off, okay, now I like writing the job. Does anyone like this writing particularly? In which case I can actually write. Anyways. So yes. Okay. Just give me a moment. Okay. So yes, we as he answered, what was one of the ways of finding out whether an object is actually at a finite distance from you? We talked about the fact that it was parallax, correct? So this is going to be a very important factor in determining distances to a lot of objects at the start. So let us talk about the most simplest form of parallaxes at the start. We can talk about something called the geocentric parallax. Okay, if you just move on the surface of the Earth, you can notice a visible difference. Now you know properly what is the size of the Earth and everything. So you can notice the angular difference in, say, the position of the Moon and stuff like that. Okay, and but the problem is the size of the Earth is extremely limited. Okay, the size of the Earth is so small as compared to the cosmic. The size of the Earth is so limited as compared to the cosmic sizes that we can't use just moving around the Earth as a measure of parallax. Okay, so I would like to put this question forward to you guys. If we are using parallax as a measure, I am telling you that we are using parallax as a measure, but we are unable to move significant distances on Earth. What movement should we use to be able to use parallax? Like, exactly. So one very significant movement we often overlook is the movement of the Earth around the Sun. That is a distance that we are covering, like on the scale of astronomical units, which is literally by name suggests astronomical unit, which is of cosmic sizes. Okay, actually not cosmic sizes in the sense that once you go to galaxies, these look like basically an ant. But the point is that you can use that to be able to calculate the parallax of stars. Okay, so a natural conclusion to what we've been talking about is that the distance to the closest stars would be measured by looking at how much the star deviates in half a year, for example, and yes, 1 AU is this much, 1.5. Okay. So we have a star. Should I draw the more realistic representation or this is better? No?
Better.
So this is the sun and this is the earth. And we notice an angular shift. Can anyone give me an idea as to how small these angular variations would actually be? You know, just an idea. कितना degrees? कितना arc minutes? कितना arc seconds? Does anyone know what an arc second is? Arc second. Do you understand what an arc second is? An arc second is basically 1 by 36 of degree. Like imagine how small that angle is. Okay, just give me an estimate. Okay, it's of the order of one
Does
arc
anyone
second.
know that in what units the distances to stars are measured?
What does a parsec mean?
Exactly. The distance at which one astronomical unit subtends 1 arc second has. So now the distance to stars are of the order of parsec you said. So what should be the order of magnitude of the parallax subtended by stars?
What? I think 4.26, na?
Yeah.
4.26 light years. This is Proxima Centauri. The name of the star is Proxima Centauri because it is proximal. Anyways, so yeah. So these distances are at an order of parsecs, which means that the angles of end are of the order of arc seconds. And as a matter of fact, you know, you would wonder that we had measured the distance of the moon and stuff like that at 200 BC. And why did it take us so much time to make the next take the next measurements to the stars? The biggest problem was the technological limitation of measuring such angles. And that was what took hundreds of years to overcome. And we were eventually able to construct precise enough instruments or precise enough technologies to be able to measure such measure such angles. You cannot rely on physical instruments. You often would have to delve in other areas of science and things like that to be able to make such measurements. And that is what precisely it took hundreds of years to develop the technology for. And by, I guess, 1600s, whatever. By 1600s, we had the measurement of the distance to the closest stars, which are, say, Proxima Centauri. And honestly, like, I don't think the people in ancient times much had a lot of time to be able to think, okay, how should I find the distance to the star? They were pretty much busy dying because of battles and nothing. But
They didn't also know that sun was the center, right?
what?
Earth moving around the sun.
Yes, I mean, they're too busy,
The
busy
church-
figuring out the biblical ramifications of
Also,
even
interesting
studying the
fact,
universe.
when this guy did these measurements, he got an idea that the sun seems quite far away and the sun seems quite big compared to Earth and Moon. So he had presented like the sun could be the center of the solar system. But then, as we know, Ptolemy came along and destroyed everything. So
Who
he
was this
said-
guy?
Huh?
Who was this guy? No, who measured? Okay, moon का.
कोई तो मस्त आदमी था कोई मेडेस करके कोई होगा मोस्टली. Anyways, so yeah, well that's that, and that's how we measured the distances to the closest stars. Yes.
So like we know the distance between these 2 points of Earth within like half a year.
Yes.
But what about if the stars move respect to each other, like the sun and whatever star we're measuring? So like let's say this move down by like twice the radius of the Earth around the sun, then we can't approximate the distance. Correct?
Your star moved.
No, let's fix the star. Like you're looking for the point of view of the star. Then the sun, so solar system would have moved down. Let's say.
So you're talking about relative motion in the galaxy. I see. Interesting. So we know for a fact that over the course of the years, over the course of the time we talk about, the night sky doesn't change much. So if what you were saying were to be the case, then the night sky would change dynamically over hundreds of years, and that is not the case. That is simply not the case. Even the effect that does change the night sky, called the precession, the precession of the Earth's axis, is at a scale of thousands of years. So this effect doesn't happen for So like one aspect of as we go bigger in universe is that the time scales also get unbearably large. So in our lifetimes, in humans' lifetime, in the lifetime of the Earth, the night sky doesn't change. No, not in the lifetime of the Earth, but the night sky doesn't change much. So that's not a concern. The relative motion of these on a scale comparable to this is not a concern.
Angular velocity of the sun about that star is significantly lesser compared to Earth about that star. But if there is
No, the Earth and Sun are moving nearly equally for that star, and they are not moving at an angle significant to this. Is my point. So yes, that's that. And so now we have measured the distances to the closest stars, right? Now we come to the interesting question: how do we measure the distance of the nearest galaxy?
If you like what you said is the motion of the stars relative to the sun, right? That is something called proper motion, and you can very well distinguish between that and parallax because the motion due to parallax is periodic with a period of time. So if you exactly look at the position of the star in the sky, the motion due to parallax would be something like this. But the motion due to proper motion would, like this entire thing would go like this. So you can break it down into two components, the one due to parallax and the one due to proper motion. So from the one due to parallax, you can find its distance.
Interesting question. Can anyone guess the name of the ellipse that that a star forms in the sky over the course of a year? What is the name? What do we call this ellipse? No, we call this the parallactic ellipse. I'm sorry, sir. Anyway, so moving on. How do you think? Is my question to you guys. We measure the distance to the closest galaxy. Now this is a challenge that we haven't seen yet, right? Okay, what is the closest galaxy? Huh? Ours is the closest major galaxy. So yes. Any ideas as to how this is a significantly tougher question, right? We will now hum ke like just moving this other. We can expect the sun to move around the sun around the sun in half a year, but we can't tell the galaxy ki, okay, I'm giving you 1,000,000 years. Okay, move across the galaxy, find me the parallax for Andromeda, and then tell me the distance. We can't do that. So what do we do? Any ideas? You're deep in thought.
Maybe time to move away from measuring angles.
Yeah, right. Angle आगे बहुत हो गया. Like the most precise instrument we have for measuring angles is Gaia, and it comes nowhere nowhere close to measuring the distances of objects in other galaxies.
It's something to be like brightness.
Yes, actually. So let's try to develop an intuition as to how we would even go about tackling the question. What do we know about that galaxy? No, like all we know. Okay, like what do we know about that galaxy? That's all. Like what do we know about it? What is that galaxy made up of? Stars. What are the stars made up of? Stardust. The stars are made of stardust. Okay. And what are stardust made of? Stardust is made up of elements, and elements whose chemistry we know. More importantly, we know how physics works there. Correct. That is the only thing that we know about the galaxy. We don't know its distance, we don't know its mass, we don't know anything. We just know that their physics works similar to us. And we can study our own physics. Okay. And what is the thing that we can observe there? No, not yet. That comes way later. What is the object that we're observing in nearby galaxies? Stars. So we measure stars. But we know. Okay. Any ideas as any more hints I give would be along the lines of telling you the solution. But knowing that we're using their stars and equating them to our stars somehow, how do you think we can measure the distances of those galaxies? Any ideas?
Shooting a straight shot,
Yeah.
But like if we look at the light that comes from the galaxy,
Yes.
we look at the elemental makeup of the stars, we know like at what part of the life cycles the stars are, and then we could know what brightness they should be near them, and then as the brightness decreases the distance, we could probably get a farther.
Okay. Amir, so that is a very nice thought. So what he essentially is pointing out is that if we are looking at the elemental makeup of the stars, we can guess that the star should be itna size because of the physics we know here, right? The star should let out this much light, and we know for a fact that if we have a light source which moves farther away with time, we have a light source which moves farther away, the light intensity that reaches us becomes lesser. So that is a way of measuring the distance of a light source. We know that its absolute intensity is this much, and this is the intensity that's reaching us. So instead of doing that, we do something else, which is a better and more sure-shot way of being able to measure. Where is this board? Where is this board? Most of the guys are sitting here. We use another thing called Cepheids. These are categories of stars called variable stars. So interestingly enough, there exist stars in the galaxy whose brightness varies periodically. Okay, there exists some physics that yields them, that makes them contract and expand periodically, which is why their brightness varies periodically. And some very smart people looked up at the sky, made some measurements, and realized that the periodicity of their stars, of these stars, and the brightness of these stars is closely linked together. When they plotted it, these turned out to split into two lines called Cepheid type 1 and type 2. And now we have a short way of finding the distance of the galaxies. What? This plot is period versus luminosity.
Log.
Okay, log of what? Which of these?
Luminosity.
Yeah, log of luminosity. So, अब बताओ, how would they go about calculating the distance of the star? Yes. So, do you guys? How many of you guys know the concept of magnitude of a star? Just show of hands. Do you know what a magnitude of a star means? No. Okay. The magnitude of a star is essentially a measure of how bright it seems to you. Okay. And obviously, the farther the star, the less bright you see. Okay. So, using the period information, they found what should be the luminosity of that star, and they saw the actual magnitude of that star, and were like, अगर इसका मैग्नीट्यूड सिर्फ इतना है, मतलब ये इतना दूर होना पड़ेगा. And that is how we measured the distance to the first galaxy, distances to the galaxies. And yeah, well, that's that. Yes.
पीरियड पता था स्टार, उससे ल्यूमिनोसिटी पता है, बट ल्यूमिनोसिटी से डिस्टेंस कैसे है?
Okay. So there is a concept called absolute magnitude of. Yes. Luminosity is essentially a measure of how much energy a star gives out, right? And you have a star, and it is giving out energy. And if you are at a distance d, the flux you receive will be equal to the energy given by it by 4 pi d square. Correct. So if that is the case, you can see for certain distances, L by 4 pi d square should give me, like, there is some log term here which converts it to the magnitude, because interestingly enough, the perception of brightness on our eye is logarithmic with respect to how much energy falls on our eye. So this is something that was actually discovered by the astronomers long ago when they invented the magnitude system. So they see that my magnitude should give me some value of this, and they find d square d by that, and they're done. Zero. So, yes, that's that. Okay. Now we will have to wrap up in 15 minutes. So, okay. So, now you've measured the distances to some galaxies, some close by galaxies. How would you go about measuring the distances of faraway galaxies? Now, what is the problem with using the same method of measuring the distance to faraway galaxies? What is the problem? The brightness is too less, bro. You can't even see the galaxy, let alone see the star. So, what do you do? Even that is not visible at if you go decently far enough. Like, or there is no light which is strong enough to.
Just to get an idea, has anyone seen a galaxy through a telescope?
Bro, it's like genuinely just a haze.
Okay, see, wait for it next semester. You guys will get it done.
Yeah, I want to wait for the night observation. So, it is not something radical. The answer is not something absolutely new. You use light sources, but what light source will you use now? Yes, that's but okay, black hole is a good idea, but the black hole is literally black. How do you see a black hole? That is right.
I mean, that is right, but the thing is, you want a source of light whose absolute brightness you know very surely. You'll be able to say that how far it is compared by seeing how bright you see it and how bright it actually is, you'll find its distance.
You want something whose physics you can study close by.
Aren't you like somehow like if you know a distance like with this method one star, right? If you know it's certain brightness, find another star with a certain brightness, see the shift in brightness and then
Yes, but that's what we talk about. We can't observe individual stars.
You can't resolve stars in the galaxy is too far.
So,
Brightness of the center of the galaxy is too variable. It's not something we can predict from our phones.
so now is when, so basically we can't see stars because they are here. But in every class of objects, there are some attention-seeking stars. Okay, so we can look for attention-seeking stars. What are attention-seeking stars? Attention-seeking stars are stars that want to be noticed so bad that they blow up. They say, I'm gonna go supernova. They come to the end of their life and go, I want to go out with one last bang, blow up. Actually, we had a small animation for that, but like that's a bit out of scope because of the time. But they essentially go supernova, and that is called a type 1A supernova. There are many types of supernovas, but the kind that we're going to talk about is a type 1A supernova. And the good thing about a type 1A supernova is that we know its maximum brightness is constant throughout all types of type 1A supernovas. And it's extremely bright. Just to give you an idea of how bright it is, the light given out by type 1A supernovas outshines the entire light output of that galaxy for something. The entire galaxy. There's like millions of stars working their asses off to give out light, and one star just goes boom and grabs all the attention. So that is a method, yes.
गैलेक्सी में like billions of stars, तो हर रोज एक तो सुपरनोवा होता ही होगा.
Like that's an interesting question actually.
The probability of a star going supernova is less than 1 upon the number of stars in the galaxy.
Yeah, I mean,
every star is a supernova.
like we've been waiting kabka that some star goes supernova in Milky Way galaxy. Please, I want to see a supernova. But like there are two stars which are teasing us like crazy. But sometimes it's like मैं अपने सामने पर्दा लेके आके इनको दिखाऊंगा कि मैं फटने वाला हूँ, but मैं actually नहीं फटूंगा. Like it's my dream in my lifetime to be able to see Betelgeuse explode. I know that's a bit difficult. And so that's that. We have a red giant who creates matter on a white dwarf, and this white dwarf is like, no, I cannot handle your problems. It blows up, and in that blowing up, it releases such a huge amount of energy that we can see it from very far. And now, because we know the maximum output of the energy should be something, this is the light, this is basically the energy output of that supernova versus time. And we know how much of it we see, what is the magnitude we observe, and that using that we can find the distance of faraway galaxies. But yet we have not reached a point where we can say that we don't need to develop new methods to find faraway things. You know, we are just like working on like wishes. Yeah, there is some event which gives us a lot of light. And you know, often that does not happen, like the universe does not work every day. So what would you do after this? Just think about it. So now I am going to tell you about, okay, so now like what are your other, so we have talked about how much light we receive, but we have not talked about the quality of light we receive. So now think of what you could do to measure the farthest galaxies that there are in the universe. And I'm sure most of you guys would have heard this in news articles, James Webb ka hua, and a lot of things. So, yes. And why would the wavelength shift?
The stars usually, the universe is expanding to stars.
Yes. So, how many of you guys attended astronomy? Oh my god. So there was a very nice question in it. If any of you want to hear about it, it was related to cosmology and the expansion of the universe. We can talk about it later. We don't have time right now. But yes, so cosmology tells you and observation tells you that the universe is expanding. Okay, and you can use Doppler effect to understand how fast the universe is expanding. And the good thing about cosmology is it gives you a model of what speeds the universe is expanding at. Kundan here was supposed to bring us a balloon to be able to demonstrate physics, but he walked into action at 5 o'clock. And Mike Yuki did not bring the balloon. He did try for one at one shop. But so suppose this is your universe, and what cosmology predicts is that this universe expands uniformly, so to say. Cosmology is actually an amazing topic for a GD itself, but we'll talk about it later. And why cosmology comes at uniform expansion is something we can talk about later. But it tells you that universe is like a rubber sheet. The universe is like a rubber sheet with infinite soldiers pulling at the metaphorical end. There is no end actually. And uniformly it changes to something. So if the universe were to expand to twice its size, the distance between any two objects would expand to twice the size. Hence, what is the relation between the relative velocity of two objects and their distance? Proportion. Okay. So V equal to D. Can anyone tell me what this constant is for? The pioneer of cosmology has his name on this constant, and this is the Hubble's constant. And using this, now we have a method of finding the distance of any galaxy whose light reaches us. We go, okay, this is the redshift. I know the entire mathematics of cosmology. I will plug it into not exactly this equation, because this equation actually has to be integrated over time and stuff like that for very far away galaxies. and that is that you can measure the distance of any galaxy you want ever in your life whose light reaches you. If the light does not reach you, तो like Einstein ने बोल दिया भाई नहीं कि मतलब ना ही measure करो तो so that is the measurement of every object in the universe. I just have one last interesting question for you, and I would like you guys to give me an answer for that. I said yes.
But like, since it's so far away, the distance won't be accurate because it will be further than what we measure the object. Because by the time the light reaches up, the object's already gone. It is further out.
So we can account for that using the mathematics we have.
That is exactly the reason you said that we need to use an integration.
Yes.
But also interesting fact, the Hubble's constant is under quite a big debate. The value of the Hubble constant.
But like we can still get it to a quite decent accuracy.
So the Hubble's constant is not actually a constant. It changes as the universe expands. So the time at which the light left the galaxy and the time at which we received the light, in that duration the Hubble's constant has been changing. So we have to integrate over
When we say the distance we measured is accurate, it is accurate with respect to what? Like, what is the reference?
Accurate, see, in any physical theory we develop, we can make sure how accurate our predictions are. we can say that this is our error tolerance, this is that, okay, and only in a few certain cases can we say that this assumption might be wrong in itself. And if that were the case, then we would actually question a lot of the things we conclude about the universe. But when we say accurate, we often talk about the error tolerance we have with our measurements and stuff like that. And just one, okay, yeah.
When the light goes, there's going to be a lot of galaxies instead of whole regions. Like, it
Yes,
might not be.
yes.
And like it's going to be a lot of mass. And then Einstein said mass is like time dilation, length contraction, all that stuff happens. Like,
See, okay, the universe is fast enough for a lot, there not to be a lot of stacking actually. You know, almost paradox की बात करनी चाहिए थी इसमें. Anyways, like the universe is not dense enough कि हाँ वो star आया बीच में mass से टकरा गया sad. It reaches us.
no, it reaches us, but like, should we, will there be some sort of time dilation or something with the present of a lot of masses like near it, why the light reaches us?
अच्छा, no.
And that
Like,
is taken into account by the when you say the
no,
universe
he
is expanding,
means that under it will touch to the gravitational effect of some.
Gravitational density and all.
okay, that is the same answer as he gave.
Yeah.
That would require
Yes.
that you have significant massive bodies in the path of the line, and the universe is too less dense.
The effect we talked about is a local chance, right? Very close to the sun.
You went interstellar.
It's not that significant. You need to have a very massive
Yeah.
object for it to even have a bit of.
Yes, and he knows, bro. He has taken the general relativity course. Vishwa here, our local black Einstein. Anyways, where was he? Actually, like color constant matters with both hair and skin. So, I was saying something. Yeah. Come on, guys. I want to drop you with another question, and if anyone can answer that,
Sweet.
you are guaranteed to be considered next year. No. But anyways, the question is, I just told you guys, you should have asked me a question. I just told you that the distance between any two objects increases by that factor. You know, if the universe is expanding twice its size, the distance between any two objects rises to twice its size. Does it mean that Kundan here is getting fatter? Does it mean that by the time the universe expands to 10% its size, his belly will also have expanded to 10% its size?
Kundan entirely will expand.
So, entirely. Like, but like, more importantly, his belly has also expanded, right?
I'll get taller by then.
You get more, you get more girls finally. But, okay. Wait. But other people think, yes. How many answers how many of you think you have an answer as to why that does not happen? I just talked about, you know, how the universe is so uniform that every effect should uniformly happen. Like, if the universe is, as a matter of fact, so uniform, you should not be sitting here. If the universe was so uniform, then every matter should be spread out entirely. And that is where quantum, like, I'll just throw the word here because that's what apparently a lot of movies as well do. That's where quantum comes in. Okay, that's why there are small fluctuations at the start of the universe which lead to you being born, me being born, Earth being Earth. Okay, and not just matter being everywhere. And that is the point. So even though the universe is extremely uniform at a large enough scale, it is non-uniform at a small scale, and what holds it together are other forces. As he correctly pointed out, the forces of electrostatic attraction between our molecules lets Kundan not grow taller and be the same size. It lets you be who you are. Any questions? And the people, like, I think that's all. We can, you guys want to leave for logics, you can. And any questions? So I am here. Yes. If you want
we can have the astronomy discussion. I just wanted to first of all thank you all for coming.